Hello. It's good? Okay, let me see. Okay, I think we're going to start today's discussion. So these are the topic we plan on discussing. Okay. Any questions? So what we're going to do is, before I start, I want to align two things. One is I got a few questions in emails that about the schedule. I uploaded a schedule which is not perfectly aligned with Professor Huang's class. So I uploaded another one because we revised the date on exams, quizzes. Therefore, I'm just going to say it again. We're going to have exact quizzes. We're going to take the quiz together on the same questions, on the same date for quiz, final exams, final midterm exams, and also homeworks. They will be all identical, okay? So the schedule will be identical, so if you have trouble, you want to go over and listen to a Chinese version of the class, it's perfectly fine. But we're gonna have the same schedule, the same exams, and same quizzes and homeworks, okay? So what we're gonna do today is hopefully to make a lot more progress on chapter 2. So the chapter 2, there's basically two main topics. One is just to give you a brief understanding as to how carriers are generated in semiconductors. So we start talking about having intrinsic and extrinsic semiconductors, and how does these carriers being generated, and how do you actually deliberately put carriers into these semiconductors to control the amount of carriers. So we're going to do some simple review on how does one manipulate these carriers, and how does you calculate the amount of carriers, especially the electrons and holes, which will, in intrinsic semiconductors, will become majority carriers and minority carriers. Therefore, the key important thing is that how do you manipulate these materials? You put in dopants, acceptors. You want to know what type is called the acceptor dopants, donors. These different type of some problem with the sounds. Different type of dopants. So you put in dopants, and then you create these eccentric semiconductors, and these eccentric semiconductors would then allow you to manipulate its carrier concentration. So we're going to talk about carrier concentration because this is the key to the next thing. So I want to, before I actually start the details on how does one calculate these carrier concentrations, the next important thing is then it has to move. These carriers moves around by two forces. One is by electric field. We're going to talk about that. This is by electric field. And the other is by collision or thermal energy. Diffusion is by collision. So it's mostly thermal dependent. So there's two forces in making these carriers particle move in a system. Because these are charge carriers, therefore if you apply an electric field, of course they will move. So there's called we call the carrier transport mechanisms. And because these carriers are charged, and when they move, then they create currents. So you then get current. So that's the key important things we're going to link to devices, because as I said in the first class, we talk about elements. Each of the elements, you want to know when I apply a certain voltage, what is the corresponding current. That's actually the key in controlling a electronic circuits. Okay? So we're going to talk about forces that's making these carriers move, drift and diffusion, and the balance between the most iconic, I should say, example in discussing these two mechanisms is actually the next structure, which is the p-n junction. So once we have the understanding of n-type semiconductor, p-type semiconductor, what happens when you put them together, it becomes a p-n junction, which is the essential core in all of the semiconductor devices. which will then lead to a diode circuit. That will be a diode element. These diode element will then have a asymmetric conduction mechanism. Then we're going to talk about the reason why it only allows current to flow in one direction and blocks the current that's flowing in the other direction. So that's sort of the link of this. How do you start with physics and then enter into the device discussion? And then, of course, this would then be applied to a circuit. So you will have a basic understanding as to how the elements moves and what are the basic underlying reasoning of this behavior of these devices. Okay? So hopefully we can start on talking about p-n junction. I don't think we can finish it. Probably takes another 2 hours on Thursday to finish all the discussion on p-n junctions. It's a relatively big topic. If you wanted to talk about the current in p-n junction, if you're taking courses like solid state electronics, it will take about 3 weeks. So we're gonna do a simple version. Okay, so I'm gonna do another simple version on a thing called, because a lot of you come up and ask about let's first review it and then I'm going to talk about that. First, I wanted to review what we have already discussed. One of the key important thing is the extrinsic semiconductor. What is it called? I misspelled it. You want to think about there's two types. One is the N type. And its key characteristic is that you dope with, we call the donor type. This is the donor type dopant or impurity. You can use dopant or impurity. This is, you dope with donor type impurity, and then we get its majority carrier. Because it's N type, majority carrier is N. If you wanted to put the note on this, it's just to make sure that it's in N type. Majority is electron, majority carrier is N, minority is P, and also in N type. Okay? So that's it. N type semiconductor, its characteristic is basically what is called the N type is you put in donor type dopants, which are the group 5, which is phosphorus. For silicon, it's phosphorus or arsenic or antimony. Is that right? Did I get it right? Indian arsenic. Okay. Okay? So then the second one is P-type. For P-type semiconductors, you dope it with, we call it acceptor type dopant. I should, a better way, you can actually just acceptors. You put in acceptor impurities, and then what happens is that the majority carriers will then become holes. PP means that it's in P-type. Let me just write it. This is simply identifying the type. Okay? So this is also identifying the type. This N, the subscript is just identifying the type. So this is identifying in which type of material, and its majority is holes, and its minority is electron. As we already mentioned last time, the reason why you would then have, if I want you to compare these, the first things you need to find out is that you need to be aware is that we discussed it last time, so I want to write it up here. In typical cases, majority carrier is always larger than Ni, which is the intrinsic carrier density, and also much larger than your minority carrier concentration. And this is also true for P-type in most cases. In PP, MP, sorry. This is for, the same statement stands for, this is for p-type. And the above is for n-type. Okay? So the reason why you would then have much, much higher majority carrier concentrations because I deliberately put in a heavily doped. This is because ND, this is typically, let me write down. This is because this is mostly ND. And this is by my engineering because I put in a lot of receptor, which is much higher than intrinsic density. As we discussed last time, intrinsic density is very, very low. So anytime you put in sizable amount of dopants, dopants will always be much, much larger than this. And the amount of majority carrier will suppress minority carrier. The reason for that is what we call, the reason for this is because of mass. Let me think about, I have enough space. So let me write down how do you find these majority and minority carrier concentration based on two rules. One is we call the charge. One of the key important thing you need to remember is that in any of these, in a piece of material, you want to make sure that your charge is neutral. It does not contain any charge, otherwise it would be a charged element. So your piece of, if you have a piece of semiconductor, is totally, the net charge is 0. So what if you think about for the n-type semiconductor, let's think about what happened. In an n-type semiconductor, what is your positive charge? The positive charge is dopant. Remember, ND. ND is, let me write it down here. So let's say if this is my dopant. If I have a dopant inside, a donor type, let me use arsenic. And silicon. Okay? So if it has one more electrons right here, so if it donates it, the electron goes somewhere else. So if this electron left, what happened to this arsenic will be a positive charge arsenic. It's called As+, right? Because one electron left it. It's supposed to be containing 5 valence electrons. One of the electrons left. Therefore, it will be a positive charge dopant. So this is like ionic, it's more like ions. It's more like ionization. We call it ionization because the electron left, therefore it will be positively charged. So you have to think of the dopants. All of the electrons are donated into the system, therefore it will remain positive charge. So if you think about it, these donor type dopants will be positive. It will be positive to the Q, ND. In a system, it's positive charge. And then there will be these electrons flowing around. These electrons are negatively charged. N plus another positive charge holes equals to 0. I don't know if let me write it over here. Because these are, let me write it in yellow. So positive charge will be the ions, ionized impurities, ionized. These are positive charge when the electron left. And then there's a negative electron, N plus. There's also another positive carriers, which is Pn. So in an n-type semiconductor, the charge neutrality should contain 3 elements. Once again, there's an ionized impurity. This is called ionized impurity. And then there's the electron, there's hole. They should be neutral. Okay? And because we already know that majority carrier is much, much larger than minority carrier, therefore, in most cases, we assume that this is negligible, close to 0. Therefore, what you get is that because of this, what you get is NN equals to ND. Right? That's how we conclude our majority carrier is dominated by the amount of non-ionized impurity, which is 1 by 1. One donate, and the electrons mainly coming from these donations. So for the same charge neutrality equation, I want to use up that space. So we can also write this is for n-type, right? Never mind, let me just use that. So let me write it here. So for n-type, I'm gonna write it again. So it's positive Q ND plus minus Q NN plus a positive, this whole Pn equals to 0. That's the equation we use. And the conclusion is, therefore, NN is approximately, actually you can, so equals to that. Majority carriers, the dopant will then decide the amount of majority carriers. So for p-type, let me use it. P-type. Does anyone want to help with this? It's the same, just a different type. So it's the same thing for, let me write it down here. So then what happened is that you have boron, and then silicon, silicon, silicon. Remember, it only has 3 valence electrons. So if there's supposed to be a hole, if this is occupied by an electron, if electron is being placed here, this will then be also an ionized impurity. It will be B minus. It's like chlorine and salt. That's like so it's like ionized impurity. It's just not in liquid, it's in solid. So p-type, let me write the same. So you have to recognize that your acceptor dopants, when it's ionized, it will become negative charge. So it will be, let me write it down, it's negative charge. Remember this boron, it accepts an electron in its empty seat, it becomes negative charge. And Na plus, it will then have positive charge holes, pp, plus negative charge Np, right, equals to 0. So charge neutral means that you count all the positive charge, all the negative charge, the net should be 0. Therefore, we do the same thing. We assume that this is approximately 0. Therefore, you get the same results, which is pp, approximately is determined by your doping concentration. So this simply tells us that the doping, so this charge neutral rules simply give us that our doping concentration will be determined, once again, determined by the amount of impurity you put into your crystal. So this is based on charge neutral. Okay, the second law we're going to follow in determining carrier concentration is, as we already said a little bit, it's called the mass action law. Because a lot of you come up and ask me why. So I wanted to spend maybe 5 to 10 minutes to give a short version as to why we have this mass action law. First, let me write it down. What is the mass action law? If you don't understand the basic underlying reason of this mass action law, you should just accept it first. So let me just say that, I want to say that this is only true at, we call thermal equilibrium. This is very important thing we use is that you assume that at this, what is the basic of thermal equilibrium? 大家知道吧？热平衡嘛，你的化学反应都是个热平衡。So if you have a ramping of rate, we're not looking at transient response. We're looking at equilibrium. So as I said, what is the thermal? Let me write the mass action law first. So it says that majority carriers and minority carriers, or electrons and holes, the amount of electrons and holes, the product of electrons and holes, equals to Ni squared. Okay? So if you think about I want to say once again, is at thermal equilibrium. At equilibrium. So this is true only at thermal equilibrium. Okay? So why is that? If you think about it, we start by talking about the amount of electrons and holes in intrinsic. We think about intrinsic environment. If you think about intrinsic environment, if I have an intrinsic semiconductor, what happens is that some of the electrons then stands up. We'll go back to intrinsic. This is also true for intrinsic. It's independent whether it's intrinsic or extrinsic. It's supposed to be true in all scenarios. In all settings, I should say, as long as it's at thermal equilibrium. So if you think about it, if one of the electrons leave the space, it would then be this. This will be an electron, there will be a hole. So I would then have electrons here. And then I will have a hole left here. Okay? So once these electrons start generated, it will not generate. There's a thermal energy that combines to break the covalence bound, so then you get these free electrons. But the number of free electrons will not continue to increase, because once the electrons and holes, numbers of electrons holes increases, so there's two mechanisms. One is called generation. Let's just say a generation rate. So it's number of electron hole pairs per centimeter square per second. Let's just define. And this is governed by the amount of extra energy. So this will depend on thermal energy. Okay? So this is one way of, it's like chemical reaction. You always have something goes one direction. So for example, I have, in this case, I have one direction, which is called a generation, which would then lead to electron hole pairs. But if you think about it, if I'm doing a reaction, there's always another counter reaction, which is electron and hole pair will then recombine. We call the recombination. So we can also define something called this is the generation rate G. And also there's a recombination. If there's a lot of electrons and holes in the system, they will tend to recombine, meaning these electrons wandering around. Once it's empty seat, it will try to sit down. So the sit down of electrons back into here, the sit down is called the recombination. This is referred to as a recombination. So therefore, once electron go back to this and form this covalence bond, both of them disappear. The electron hole pair disappear. So there's we can call something called the recombination. So this is a dynamic process, meaning that you have constant generation and you have constant recombination. And in thermal, so there's a defined by something called R, which is also number of electron hole pair being recombined per centimeter squared per second. It's a rate. Okay, so you can think just by common sense, you will know that recombination R should be proportional to a reaction constant. Let's just say give a constant and amount of materials allow us to recombine. So this is just a constant. This is a reaction constant. Okay? So then at thermal equilibrium, what happened is that what does it mean by equilibrium? Meaning that there's no more addition of electrons and there's reach a balance. So at thermal equilibrium, I should say that equilibrium just to be. What happened is that the amount of generation should equals to amount of recombination. And because generation has come from thermal energy, so if under a certain fixed temperature, the generation rate should be fixed and should be the same independent of material. Therefore, you get K M times P equals to G. G is a constant, and it's only governed by and only depends on temperature. Or external energy, if you have like thermal generation or optical generation, that'll be other things. But let's just assume that the external energy coming into the system is only temperature. So then you get MP is a constant. And how do you benchmark it to this? Is just to use a example. Where's the easiest example, which is in intrinsic case. So it should be independent of its material. It should be dependent only on the energy that's put into the system. So we use a benchmark, which is the case where N equals to Ni, P equals to Ni. In intrinsic case, therefore, it's Ni squared. So we use this as our benchmark. Use the intrinsic as a benchmark because you want to find a calibrated point. So we just use the intrinsic material. Therefore, you finally get the mass action law. I hope that this helps you understanding why we get this law. And because of this law, then we can actually follow up on finding out. So once again, charge neutrality equations allow us to find majority carrier. And your minority carrier concentration is then determined by mass action law. So we go back to 10 minutes, right? 10 minutes mass action law. Okay, so let's think about, so how do you find minority carriers? So once we have our majority carriers, we just follow these rules. So minority carriers for N-type is holes, is Pn. Pn equals to N squared divided by majority carrier concentration. And because this is governed by doping, so we know for N-type, your minority carrier concentration, well then the number of holes will be determined by Ni squared divided by Nd. And this is typically, as I said, smaller than Ni in most cases. You can also do the p-type. I wanted to, okay, p-type, yeah. So for p-type, it will be MP which will be Ni squared divided by Pp. And we know that in p-type semiconductor, this dopant acceptor, so it's Na, Ni squared. And this is also smaller than Ni, smaller than Pp. Pn. Okay? That's good? So once we have this laws and allow us to find out the amount of electrons and holes, I hope I'm not moving too fast. Is it good? Because if everyone is agreeing on carrier concentration, then we're going to move on to the next part, transport. But before we do that, I want to do something relatively small. See if I have any space for this. It's good? Okay. In most of the semiconductor material, did I make a mistake? NaPP. Yeah, you're right. This is p-type. This is N. Sorry. Majority carrier. Okay. Any questions? Oh, my eyes. Okay. I want to discuss something. Is that in common practice, what happens is that you go buy a piece of wafer. So if you start with a wafer, we typically refer to, let's say, silicon wafer, or sometimes referred to as a silicon substrate. So we start with the silicon substrate. It comes with a certain amount of doping. It's typically pretty light. Let's say if you get we said a p-type substrate. So meaning that it started with a Nn, let's say 10 to the 15th. This is fairly lightly doped, and it's a typical number for p-type semiconductor. For substrate, I mean lightly doped substrate. If this is, so for 10 to the 15 to 10 to the 16th, this is typically referred to as lightly doped. So sometimes you will see something labeled as, I don't have a space for that. But this is typically, I'm doping it with 10 to the 15. It's lightly doped. So it's typically referred to as a P minus version. P minus simply referred to as lightly doped. It can be M minus or P minus. So the minus sign simply means that it's lightly doped. Okay? So you start with a P minus substrate. So sometimes this will also be referred to as a P minus substrate. So this will give you that it's p-type dope, but it's lightly doped. It's in the range of 10 to the 15 to 10 to the 16th. That's generally referred to as the lightly doped version. Okay? So if I want to make a structure on top of it, what is typically being done is called a counter doping. So if I wanted to make a I have it. Let me expand the version a little bit. So I start with a substrate. So this is also referred as P minus version. Okay? So if I wanted to make the surface another type, meaning that I start with a P minus, I want to make it into an N type. That's how you make PN junction. So I want to introduce additional dopants here. So for a certain region, I wanted to make it N type. So I introduce a ND of 10 to the 17th, for example. So I put additional dopant into this region. This process called counter-doping. So what happened is a little bit like ionized, I don't know the English, but it's like 酸碱中和嘛，就是you combine it with, you start with a acceptor type and then you add a donor type, so that counter the effect. Therefore, the net doping in this, and because this is slightly highly doped, so this is the N region. You call the N region. And in this region, in the anti-region, anti-counter-dope region, we call the net doping will then become ND minus NA. So you then have a net doping of ND minus NA. And this would then determine, because you have to counter the impact of the original p-type doping, so this will be your NN in this region. It will not be ND itself. You have to subtract the underlying background effect of these NA, and this will be what we call the counter doping. Okay? And of course, you could dope it even heavier. So what I can do is I can do another counter doping if I want. So for this, if I want to make a, we call it bipolar junction transistor, I might dope a little region here with another heavy dope, we call it P plus. If I do another P plus with a doping of Na, let's say 10 to the 19th. This is just to give you a sense as what is P plus? P plus stands for, I don't have enough space. I'm thinking about where to move. So I want to emphasize once again for P, for plus. If I'm saying P plus or M plus, this is referred to as, we call the heavily doped region. So then it will be something close to 10 to the 19th to 10 to the 20th. I'm using the plus number. So I can also counter-dope this region to an even higher dope P. And this, in this particular region, it will become P-type again. And it's, so what we're concerned about is the amount of carrier concentration in this region. So if I want to write a PP, it will be NA, because I have two NAs, therefore I want to label it. This is NA1, this is NA2. Let me write it over. So for this region, it will be NA minus ND plus NA2. Okay? Is that clear? So you add all the acceptor minus all the donors when you want to get the final results. So you counter dope it twice, right? But you already, your background is 10 to the 15th, so 15th. So it's 10 to the 15th plus 19 and minus 10 to the 17th. But then it will be approximately, the heavily dope will dominate. So you will see something, Na2 will dominate. Okay? This is good. I have a very small space for this. Sorry about that. This is, so the key things to take home is that you need to understand what does plus means. simply referred to as heavily doped region. Minus means lightly doped region. And then if I just simply label it N or P, it will simply be just middle range doping. So then you'll be able to read something like this. For a MOS transistor, it will be something like this. It would then be a P region, M plus, M plus. Something like this. You will know that you start with the P and then you have two contacts with N region. M plus meaning that's heavily doped. Okay? So once you see the structure, you get a sense as to these are the counter-doped region and these are the basic substrate. Then in integrated circuits, you will see many counter-doping. It will contain layers of dopings and then counter-doping of materials and allow us to form certain structures. For in this case, we'll then have, if I'm looking through here, if I'm magnifying it to, then this will be, if I'm drawing it out, it will be, this will be a P plus region, N and P. So that will give us a bipolar junction transistor. So that's what B and P. Okay? So through different modules of counter-doping, we'll be able to form structures like transistors along the way by using these techniques. But we're not going to talk about that until I believe chapter 4, we start talk about bipolar junction transistor. We're simply going to talk about two counter-doping that this will just give us an PN junction as our next topic. The topic next and next. It's good? Any questions? You guys looks, you following okay? I should ask you some questions. Okay, so we're moving along to the next part, which is transport. So as I said, once you know how to have the basic understanding as to how to put extrinsic, how do you actually control the amount of carriers inside a piece of semiconductor, the next key important thing is to understand how these carriers move, allow us to get the most important parameter, which is the current voltage relationship. So we're going to talk about carrier called the transport mechanisms. So carrier transport, there's basically two ways. One is called the drift. And drift is typically done by charge carriers. It has to be charged carriers in a electric field, inside an electric field, because these charge carriers will then be pulled by Coulombic forces. So think about it, if I have electrons, these electrons, as I said, we have carriers. We could assume they're not really free, like free in space. They're free like, they're not bounded by covalence bound, therefore allowed to move. But when they move, they're encountering some sort of collision. So there's a limited speed. There's a limitation on its behavior inside the crystal. So electrons moving in silicon crystals. Okay? It's not in free space, but similar to in free space, but there's some collisions within these type of transport. And the other thing is that it's called diffusion. As we know, diffusion is not limited to charge carriers. It only depends on what determines diffusion, if you think about it. What determines diffusion? Correct. So diffusion is pulled by, we call dndx, dpdx, which is carrier is controlled by its gradient. So the gradients of these population, gradients of your carriers, will then determine the force of diffusion. Okay, so it will be independent of charge, but because the movement of these carriers is a charge carrier, therefore it will conduct current, but it does not require a field to pull it. So what is the force behind diffusion? What is the force behind? You know that it's determined, it's proportional to gradients, because if I'm wearing perfume in front, you would then smell it in the back, because why? It's actually being pulled by collision, as I said. There's more, the chances of collision in front because the population is denser in the front. So the collision is actually initiated by thermal energy. So the forces in diffusion is also still in thermal energy. So if you think about it, if you're sitting next to a person wearing perfume, which will be, I wouldn't say worse, but because I hate perfumes, but in the summer or the winter, you would then smell the stronger smell. In summer or winter. Like in winter, during the cold, if I'm wearing perfume, you probably wouldn't be able to smell it because the diffusion force is less because there's less collision between these particles. So this would then depend on, I want to emphasize is that it actually depends on thermal energy of the system. Think about it if you go to South Pole or something very cold, and it's not very effective in wearing perfume because it will not travel too far because the diffusion is being limited by the amount of thermal forces that's being driven these sort of diffusion. We're going to look at diffusion. Going to look at that a little bit. So you can think about the underlying energy source. One is from electric field. The other is actually from thermal energy in the system. So let's first look at drift current. So this is the same thing if you go to courses like semiconductor physics. It will take maybe half a semester to talk about transport mechanisms. There's a lot of scattering events, that sort of things. But we're going to skip that and just to give you the results. So what happened is that if you think about it, I have a piece of, let's start with the drift. If I have a piece of substrate, silicon substrate, let's say this is my N-type substrate, is medium doped. So if I give you a piece of N-type substrate, you know that it's being doped with what? Donors. And then it's doping. If I'm labeling this, you know two information. One is that it's doped with donors, whatever's coming in the N-type silicon substrate. So will be either be phosphorus or arsenic. Okay. The other thing is that it's not heavily doped or lightly doped. It's in the middle range. So you're supposed to get that information simply by this simple statement. The other thing is that I will then have, this means that my majority carriers is what? Okay, this will come in quizzes. For example, I will ask you questions like, if I have an N-type substrate, I'm giving you this information, you should be able to answer dopant type. You should be able to say, to get an answer as its doping level, as I said. Approximately doping level, and then majority carrier. Okay, so first the dopant, what is its dopant? Just give a number. I already said that. So what is this? Does anyone want to answer? Just give an answer. What is it? It's possible dopant for the N-type semiconductor. Yes? Yes, arsenic. Okay, so doping level, just give a number. It's not this or that. So what do you think? Just give a number. Anyone want to just give a number? Yes, it's 10 to the 17th. This is good. Majority carrier. Electrons or holes? Electrons, correct. So once you take the course, you should be able to answer these questions, okay? So if I ask you a trick question in minority carrier, don't be tricked, okay? Okay, so once you have that, we know that there's a lot more electrons. So in most cases, you only, for drift forces, you typically only look at majority carriers because they're the dominant carriers. So once there's an electric field, if I'm applying an electric field in this direction, where does the electron go? Opposite direction. So electron should move in this direction. And it's moving, there's a ultimate speed of moving. So what happens is typically you will observe. You take a piece of semiconductor, what happens is that if you monitor the speed of carrier's movement, the speed of electron as a function of electric field, we'll actually get a curve like this. When the electric field increases, you expect the speed of electron actually increase. And this slope is typically refers as mu n. It's called the electron mobility inside a material. So these are typical a material constant in the unit of, let me write down, cm squared volt per centimeter. Okay? So I think we'll stop here for a 10-minute break, and then we'll come back and look at how this would then affect the current in the system. Let's continue our discussion. We'll leave the questions later. If you have any questions, just come back. You can come back for a question later. Okay, apparently there's a lot of questions regarding this part of discussion because I only have small spaces. I'm supposed to expand it to a larger space. But let me just clarify what happens. So let me redraw this figure. So first of all, I'm just going to give the definition. It's not a hard rule, it's just more like a experience, based on experience. Typically, what happens is if you have your doping level, which is less than 10 to the 16th, we'll refer this region either N minus or P minus. If it's between 10 to the 16th or to 10 to the 19th, it will be around NP. You will see label like that. And then if it's above 10 to the 19th, if anything above 10 to the 19th is referred to as M plus or P plus. So these are indication of lightly dope, this medium dope, and these are heavily doped, okay? And the other thing I want to mention is that whatever doping you put into the system, there are very, very few. So if I'm simply drawing a figure like this, let's say arsenic. What is to the right is all silicon. Like this. I just don't want to spend too much time drawing this. The point I'm trying to make is that this is very, very rare. Even in heavily doped material, remember the silicon atom density is 10 to the 20. Silicon atom is 10 to the 22 per centimeter square. Meaning that if I'm doping it with 10 to the 19th, you will only see 1 atoms per 1,000. So this is very rare. You don't want to dope it to change the background silicon. The background is still silicon, just a few of them, placing around in the crystal. Okay? So I'm not saying that all of the repeat. It's just a few of them within a large population of silicon. So you only have a few of them. That is just to say that all your densities, electrons and holes and dopants are much, much less than the crystal density. The crystal density is the highest among the all. So you have a background of silicon backbones. You're just simply putting a few of the dopants. Even with 10 to the 20th, probably we dope to the 10 to the 20th is probably the limit. This is the, as I said, there's a solid solubility. It's 那个溶解度，它有个 highest level. Otherwise, you're changing the material. So you cannot put in too much to alter the background silicon. So it will be less than 1%. Your doping level will be always. So doping will be less than 1%, I should say. Less than 1% of silicon in terms of density. So whatever heavily doped will not exceed that level. Otherwise, you're changing the crystal structures. Okay? So back to this part. So if I'm starting with a lightly doped substrate, as I said, if I'm starting with a P region, P minus region, And this is Na1. And then picking up a particular region to do a N-type, which is P, we'll call the N region, which is with the ND, doping concentration. And then I'm picking out another region to define a P plus with Na2. This whole process is called counter-doping. And anytime you have a counter-doping, you want to figure out in each region, there's region 1, 2, 3, right? So we start with 1, 2, and 3. So this is region 1, which is M minus. This part is not counter-dope, it's just a net doping of Na. So it's majority carrier, it's a p-type majority carrier, doping concentration is given by its doping, majority carrier concentration is given by its doping concentration, which is Na. Okay? And in region 2, what happened is that you then have something called a counter-dope, because you start with p-type and then change into n-type. So it's becoming n-type, its majority carrier concentration will then determined by this. This is referred to as the net doping. If you have two types of dopants inside a region, that's your net doping. So your net doping should be the higher one minus the lower one. Okay? And then what happens is that if I dope it again, so what I do, how do you actually find out it's doping, net doping? What you do is that you add up all the acceptor doping. So this is the total amount of acceptors, start with the background Na1 plus Na2 and minus Nd. So this is your total acceptor. And then minus total. If I dope it twice, I'm just going to minus total donors. Okay, this also works for if you inverse types. Okay, so the idea of net doping is if you have both N and P inside a region, we call counter doping. Net doping is that you can dope it 1 and 2, 3 times. This is your net doping. This is also called the net doping. If I'm only doping, if I'm leaving this will be the net doping. Net doping is just you count how much it functions as an active dopant. Okay? Is it good? Is it clear? Okay. So we're going to come back to transport mechanism. As I said, what happened is that if you think about carriers that's moving along electrons. If you think about an electron, this is an electron and I'm applying a field, electric field going to the left. That's just assuming that the electric field going to the left and electron is moving to the right. The electron is moving to the right. So if I have a electron in free space, what do you expect? You accept a force because this will carry a minus Q. Therefore, it will be a coulombic force. Let's leave the direction out. This is the force. Let's just leave the direction out for now. So the electron will experience a coulombic force to push it to the x plus direction. So then you would Newton's first law tells us that they will then experience an acceleration, right? It will be accelerated by F equals to ma. So A will be F divided by a mass, which is the electron. We call it the electron mass or effective mass because the mass is not the same as the one that is in free space, but we're going to talk about, we're not going to talk about that. Just we assume that the electrons will then have a electron mass. So that will be your accelerated time. So what determined the speed then? So you ultimately will have your speed will be determined by a times what? If you think about it, it's not if my electron is moving in free space, what will determine the speed? No determination. It will be accelerating and then it will blow up, right? But in real cases, in a crystal, remember my electrons are not moving in free space. It's moving inside the crystal. So it will then have an accelerated, we call it lifetime. Or sometimes you will see this referred to as a mean free time. I don't know if you guys familiar with this word. We use that a lot in physics, is that the electron remains free for only a duration. It looks like free for low duration because within this time it can accelerate freely by this electric force, but then afterwards it will then hit something. It will hit the crystal, it will hit itself, it will hit the minority carriers. So, the impurities. So it will hit a bunch of things. So once it hit, it will reset the acceleration process. Therefore, it would experience a mean free time. So if I want to find out the mobility, let's say this is the electron moving speed. So this would then be your speed, will then be determined by Q, E, divided by your mass, and then time. So finally, we get this, and this. That is why you get a constant. So this will then become mu n E, where mu n is defined as the slope. As I said, this is the slope between the correlation between speed and electric field. So this is called electron mobility. I think I will already write the unit. This is the mobility unit. Okay? So it actually depends on, if you're looking at an equation, it would depend on constant governed by effective mass called ME is the electron. Typically referred to as effective mass because its mass is not the mass in free space because of its movement and inside crystal. And tau is the lifetime. I'm just going to use mean free time. And typically between collisions. So how long does it look like free before it hits another thing? So this will then determine by what? I just want to mention a little bit on mobility's dependency. Mobility, you could, if you go to a textbook, solid state device textbook, they will give you mobility. So you will find carrier mobility. There's mostly mu n is 1,3. This is the typical number we use. And there's two types of carriers. We have electrons and holes. Holes also moves. Which one will be higher? What do you think? Which one will move faster? Electrons move faster or hole? Of course, yes, you got it right. Because hole is the movement of seats, empty seats. So it takes a lot of electrons to combine combine the movement. So in typical cases, I want to say it again, in typical scenarios, mu n equals is a lot higher than mu p. This is about 5. Let me get the number right. 480. I'm going to use 480. About 500, but if you look it up, This is for silicon. This is typically referred to silicon bulk. Silicon electrons and holes bulk mobility. So this is about 480. And you will see that this is typically set at a room temperature, about 300 degree K. So the reason why I'm saying this is that, first of all, you have to recognize that, as I said, electron mobility is typically higher than bulk. Electron mobility is typically higher than hole mobility. The other thing is that it will depend on temperature, because temperature will be affected by the mean free time. Because if you have a higher temperature, the chances of you hitting a covalence bound is higher, because the covalence bound is bouncing in a higher frequency or higher magnitude. So there is a much better chance that you will then hit something. The other key important things in this phrase, so this will tell you that mobility depends on temperature, and also mobility depends on structure. Does anyone know what bulk means? Bulk. I assume that someone knows what bulk means. What do you, when you use this word, I'm still trying to think. It's not very commonly used in everyday life, but if you go to Costco, you buy things in bulk, meaning that you buy things in large quantities. So bulk in this case simply means a large piece of semiconductor. So this is like, the reason why it's being highlighted is that if you're running in a large piece of crystal, the chances of collision is governed by the crystal itself. But for devices like, especially MOSFET, you're moving at the surface, so you have something against. So this is bulk mobility, so sometimes we will have something called a surface mobility. But what we mean by surface mobility is that if your carriers are moving along the surface, it's a different story. So that you'll be collided with the surface a lot, so then it will moving in a much lower speed. So typically, bulk mobility is the highest of all. You will see numbers even lower in conditions where it's more confined, and there's a lot of additional collision or scattering events happening. So the way to think about it is that bulk mobility is how fast can you move if you're outside in the field. And surface mobility is more like in a confined classroom or channel, which will then, you will then be limited, therefore the mobility will be slightly lower, even lower than bulk mobility. So I'm just trying to say that this is the most optimistic number you get in semiconductor material. So it's sort of like the upper limit of mobility. It's very hard to obtain this ideal. These are more ideal numbers. Okay? So with these ideal numbers, let's do some estimation as to what does this refer to. So once we have the mobility, and if I give you a structure, we can actually estimate how fast a carrier can move between two terminals. So I'm just going to give you a very simple example. Let's say, did I miss something? Okay. If I have a piece of silicon, which is, and the thickness very thin, simply 1 micron between the two terminals, and I'm applying a electric field. I'm giving it 1 volt, and I want to see that how fast does the electron coming from this terminal, the current is moving this direction, the electron coming from this direction, how fast does it cross this piece of silicon and reach to the other side? Okay? So let's say if I have a N-type silicon. Okay, I don't need to give you a doping concentration. You should be able to find out how long does it take. So how long does it take? Delta T. From here, the average speed of average time an electron take from moving from terminal 1 to terminal 2. Terminal 1 to 2 to 1. Okay? So from 2 to 1, how long does it take? So what you do is that you estimate the speed. So how does one get speed? Well, from this, you get speed. Electron speed is its mobility times field. So we know the mobility is, we're just going to use the number. The unit is cm squared per second. And then what is the electric field across this piece of semiconductor? Electric field. What is its field? 电场是多少? V over L, correct. So it's V is 1 volt divided by 1 micron. This is electric field. I'm just, okay? So once we have the numbers, you could actually get it. The speed is about 1.35 centimeter and 10. So you get the speed. Once we have the speed, then you simply look at delta T is, let me get the number. The L is 1 micron divided by the speed. It will be about 10 picosecond across 1 micron. Okay? So you get a sense as to how fast an electron can simply transport from one direction, one terminal to the other. Nowadays, the distance between terminals are even shorter. But this is not the ultimate limit of speed. We'll have other limits, but this is the, I should say, the upper limit of speed. Okay? So you get a sense as to how does the affect the transport of carriers and how long does it take to transfer from one place, one terminal to the other, simply by drift. Okay, the next thing is that aside from knowing how fast can it move from one terminal to the other key important parameter is how does it affect our current. So then I probably need this to make sure that I don't make a mistake. So we want to know the drift current. That's the key important thing. So the next thing we're going to do is to calculate drift current. The amount of drift current or the level of drift current in a piece of semiconductor. So to find drift current, we need to define a cross-section. Anytime you want to find current, you want to find out the amount of carriers and how fast does it move along the way. So let's define a structure first. So we start with a piece of material. And there's the width. Let me define that. This is the width. This is the length. And there's a finite thickness of the film. Height. My drawing is bad, but bear with me. I want to make sure that the thickness are okay. So you can see that is a piece of material. Okay. So the way to do this is that we want to define a small little region of interest. So you assume that you're looking at carriers only in the limited region here. So I'm just trunching out a small piece of dx. Okay? So the amount of charge within this material within this box, the blue box, will be delta Q. Will depend on the width, the total area, total volume of this block, which is W times delta X times H. That's the total volume of this region, and times the amount of charge. So the amount of charge is minus Q. Let's use the N-type semiconductor. So the density of a carrier, amount of charge it contains, the volume of this region. That will give you the delta Q within this blue box. So what is I? By definition, I is Q divided by time. How fast does a charge move along within a particular time? Okay? So this will then be minus Q. I have minus Q times N W H dt. So I'm changing the time into dt, therefore this is dx. Right? dq dt. So what do I get is this term. What is dx dt? Velocity, correct. This is the velocity. And because the velocity is moving, so we then have, if I'm going back to giving it the direction, my current will then be current. If I want to find current density J, it will be current density divided by cross-sectional area. What is the cross-sectional area? It's weird. Cross-sectional area is WH, correct, WH. So divided by WH, so you put in back this equation, it will simply give you minus QN dN dx. So this will be minus QN. This will be, we know that this is the speed. Let me write it down. Electron moving speed. And it will be minus QN mu n e. The reason why we don't have the minus sign is because electrons moving in the opposite direction of electric field. So this direction is, if I'm writing down the equation, it should be mu n e. Because it's electron, therefore it's the moving direction is inverse, opposite of electric field. Therefore, I'm putting this back down. Therefore, you get a positive sign. Ephron. So then we get the final equation. Let me write down the equation. The equation for electron current density will be Q n mu n e. So current direction is the same as field direction. Right? Okay. So we can do the same exercise for holes. Let me write it down. So that's electron current density. Let me write down electron. Let me be specific. Electron drift current. Will then be mu n Qn mu n e. Okay? So we can do the same thing for Hall drift. I want to be specific because we're going to have other type of current. So Hall drift current density will then be mu p, qp, mu p. You can do the same exercise and get the results. So your total current, J total, will be Jn plus Jp. Anytime in a piece of semiconductor, you always have holes and electrons. There's always holes and electrons. If I ask you a question in the n-type semiconductor, the minority carrier, they're always, because Np equals to Ni squared. So even though it's very low, they're still there. So you want to make sure that if I ask you, is there hole current in a p-type semiconductor? Yes or no? Yes, but it's just very, very small. Okay, so just to make sure that even though we typically ignore them, but they still exist. Okay, so electrons hole. So let me write it down. So the equation would then become Qn mu n plus P mu P E. And remember all Ohm's law. It tells us that this is what? Conductivity. Remember our first class? Conductivity, that's Ohm's law. So it will tell you that the conductivity of a piece of silicon will depend on Q n mu n plus P mu P. Okay? So for n-type, silicon, what happened is that we know that n much larger than p. So your sigma will be Q n mu n. And it will be Q. Yeah, let me write it down. These are mostly constant. And it will depend on your doping level, right? For p-type, P much larger than n, therefore your sigma for p-type will be P mu P. So it will be Q mu P. Let me emphasize again, these are mostly constants. So mobility, there's a slight dependence on temperature. You can probably ignore that, but these are typically constants that we can use. And then it only depends on your receptor doping concentration. So doping concentration will dominate the overall behavior, your conductivity, which is the key in controlling a material. Okay? So we can actually do the second, the third. So we have n-type, p-type, and what are the type that we have already discussed? N-type, p-type, and what? Intrinsic. So let's think about intrinsic, what happened? In intrinsic semiconductor, what N equals to P equals to Ni. So you should be able to actually find its conductivity. Its conductivity will be Ni mu n plus Q Ni mu P. So then let me write it up here. So what happened is that you will then get something like this. It will be Q Ni mu n plus mu P. So in all these three types of semiconductor, its conductivity is mostly, which one is most sensitive to temperature? What do you think? Which one? In most of these cases, as I said, there's sign dependent, temperature dependence on mobility. If we ignore that, your conductivity mostly depends on carrier concentration. In these two type of material, your carrier concentration is fixed. Whatever the amount I put in will determine, mainly dominate my carrier concentration. So the carrier concentration remains relatively stable. As we already said, your Ni is strongly depending on T over 1/3 and exponential something. I don't think maybe I had the equation right. So there's a very, very strong temperature dependency. Therefore, if you change your temperature, operating temperature in intrinsic semiconductors, it will actually fluctuate a lot because it depends on intrinsic carrier density. But if it depends on the dopant I put in, whatever I put in is whatever I put in. It doesn't really change with environment. So it's much more controllable and much more stable towards the environment. So you can see the difference in which determines or which actually allow you to control what is key to the performance of your device. Okay, good. I don't. So you should definitely do some exercise on finding out conductivity. If I give you a particular doping concentration, you should be able to find out conductivity. Do some exercise on that as well. So we're gonna move on to, hopefully we get to at least finish the next transport mechanism, which is diffusion. So let's look at diffusion. Diffusion is happens when you have non-uniform doping concentration. So diffusion happens when, so the second transport mechanism is diffusion. So when do you get diffusion is that when the population or densities are uneven. So this happens when there's non-uniform carrier concentration. This can be transient or it can be fixed. For example, if you have a p-n junction, you would then have permanent carrier, non-uniform carrier concentration on both sides. So then you would then have constant diffusion current. Or the other thing is that if I inject carriers, for example, if I put in electrons at a particular location, allow us to generate, for example, if you have a piece of silicon and then you inject photons on top of it, it would then create generation of electron hole pairs. So you would then have non-uniform carrier concentration. And it would then, the carriers will then flow from high density to low density regions, right? So this is the simple law of diffusion. So it's actually being pushed by a gradient. So typically we know that what happened is that you would then have Jn would then proportional to dn dx, and Jp is also proportional to dp dx. The movement or the flux of carriers would be proportional to the gradients of the carriers. And typically this is being given by a parameter called diffusivity. Let me define it. So let me just draw a figure first. So then if I'm plotting n as a function of x. So for example, if I'm having a level of n, a level of carrier concentration at x equal to 0, which is here, and this is the distance L. And at this particular point, typically it's governed by some particular structures allow us to keep it to 0. So then I have a gradient like this. So this is the amount of describing the profile or distribution of n electrons along a distance, along a direction x. So that would then give us a gradient of dn dx. Okay? So dn dx will then push the electrons from high density to low. So the electrons will move. The electrons will move here, from here to here. Right? The moving direction is this, but the current direction, this is the current direction. Electrons moving in the right direction, but the current is moving in the left direction. X. That's diffusion of holes, diffusion of electrons. Well, we can also do an exercise of diffusion of, let's say, holes. So you can do the same thing. Let's assume that this will be the profile of px. P as a function of x. And this is at a level of n1, n2. Okay, so then you would then have a dp dx, which is positive, but the carrier is moving in this direction. Electron current is moving in the same direction because it's positively charged. So the positively charged holes will be moving in the same direction as the diffusion direction. So because of that, we can actually write our equation of Jn will then be Q diffusivity dn dx. Okay? The reason why there's a, let me try to write it again. The reason why you get this, so the way to write this, one is the carrier. We have electrons, therefore it's a minus Q. Constant is dn. And it's moving in the direction which is inverse proportional to diffusion gradients, because dn dx is increasing. This dn dx is decreasing, but it's moving from high to low. So the direction of diffusion is inverse to the direction of gradients. So there's a minus sign. That is why you get this dn dx. Okay? So the same thing, we can do the same thing for holes. Holes are positively charged, but diffusion direction is always the inverse of its dp dx. Therefore, you get a minus sign up front, because it's a positive charge. But the moving direction is always inverse to the gradient's direction. Okay? So we can actually find diffusion currents as well as do some exercise on diffusion current. Let me see. Okay, how? So let's do an exercise so you get a sense as to how to find these things. So if a particular structure is given, you should be able to find out your diffusion current. What is the amount of diffusion current? And drift current as well. So let's just do the diffusion current here. Let's say if I have a material, as I said, at x equals to 0 and at x equals to L. So this number, let me give the numbers. Okay. Do I have a number? No, I don't. So let's just use this example. So this is n, this is 0. So we then have, how do you find the gradient? The gradient is dn dx, which is, by definition, is this minus this and this minus that. So it will be 0 minus n and L minus 0. So this is the distance, this is the difference in concentration. So your gradients will be a minus sign, which is minus n divided by L, right? So then I'm just going to use my electron diffusion current equation, which is Q dn dx. So this will be a minus Q dn in L. So once you know the carrier concentration, how long does it take to drop to 0, this gradient will then give you the current. And as I said, because electrons is moving in this direction, current is moving this direction, current is moving. So this minus sign simply means that current direction is minus x. It's moving in the opposite x direction. Okay? This is the direction of diffusion current. Okay? Oh, I forgot to mention one of the key important things when I introduced this is that we're using another parameter called diffusivity or diffusion coefficient, diffusion constant. I think textbook used diffusion. So dn and dp are diffusion constants. It's in the unit of centimeter per second. And these diffusion constant, how does we find out the diffusion constant should be different for electrons and holes because it will depend on the type of particle there is. So if you think about it, the diffusion constant, diffusion is actually be pushed, or diffusion is actually be forced by thermal energy. So that, and the other thing would then, depending on how fast can a carrier diffuse, will then depend on how fast can it move. So there's a relationship between diffusion constant and mobility. So I'm just going to write that down. So this is called the Einstein. So Einstein come out now. Relation. This relation tells us that diffusion constants and mobility are constant for all particles. And it's proportional to kT over Q. This is actually proven by kinetic energy and when a carrier is moving in a population. Okay? So this is typically referred to as VT. We're going to use this term a lot. KT over Q is called the thermal voltage. It's 26 millivolt at 300 degree K. So we're going to use this term a lot in follow-up current equations. You will see that in diode current, bipolar current equations. It will depend on, because a lot of the balance between drift and diffusion will then come up, will be proportional to the thermal energy. It's correlated to thermal energy injected into the system. Okay? I'll try to explain this again, is that, once again, your diffusion, what determines the diffusion will depend on how fast can it move and the background energy that pushes it. So the background energy is thermal energy. Thermal energy pushes these carriers to move, and its movability, the ratio between the two will be a constant to the energy being injected. Okay? So I want to give a short summary on before we go. Let me borrow 5 seconds, 5 minutes. Won't be able to get it down. So I'm just going to give a summary as to the currents that we have already discussed today. So there's the drift current. And for electron, it will be depends on carrier density, mobility, and field. For holes, it's the same, just a different mobility. And we know that NP is at the ratio about 1/3. So just to give you a number, there's a this is also at room temperature. So we all have these parameters at room temperature. For diffusion current, we have Jn, which is because of the carrier carrier type, and also diffusion is diffused in the opposite direction of gradients. Therefore, you don't get a minus sign. But for positive charge, you get a minus sign in front. Okay? And this is also at, for silicon at 300 degree K, we get Dn equals to 34 cm. Just to give you a number, and diffusion constant for holes are about 1/3 lower. Okay? So just to keep in mind that these equations, you should have a basic understanding of these equations, and we're going to use that a lot in the follow-up analysis of, especially in p-n junction, the balance between the two will then create a junction between the two type of material. Okay. I think we'll just end it here today. I was hoping that we're going to go into p-n junction, but well, we'll come back and we'll talk about more interesting structure when P and N meet. And then these two forces, whatever you have learned today, we're going to use them coming up, because these two forces are the balance in a junction. Okay? I'll see you on Thursday.